Ladies and gentlemen, welcome to a journey not through the stars, but through the unyielding barriers that stand between humanity and the red planet. This is why we will never reach Mars, a science-based exploration of the insurmountable challenges that render human settlement on Mars an unattainable dream. For decades, visionaries like Elon Musk and organizations such as NASA have tantalized us with promises of interplanetary colonization. Yet as we delve into the physics, biology, engineering, and economics underpinning this ambition, a stark reality emerges. Mars remains forever beyond our grasp. We will examine the scientific evidence that supports this conclusion, drawing from peer-reviewed studies, expert analyses, and the harsh lessons of space exploration history. Let us begin with the most fundamental obstacle: the sheer distance separating Earth from Mars. At their closest approach, known as opposition, the two planets are approximately 55 million kilometers apart. However, this alignment occurs only every 26 months, and even then, the journey would take 6 to 9 months using current propulsion technologies. Chemical rockets, the workhorses of modern space travel, rely on the Hohmann transfer orbit, a fuel-efficient path that minimizes energy expenditure but maximizes travel time. Consider the physics. Newton's laws dictate that accelerating a spacecraft to escape Earth's gravity requires immense thrust. Yet once in transit, the vehicle coasts through the vacuum of space at constant velocity. To reach Mars, a spacecraft must achieve speeds of around 11 kilometers per second relative to Earth. But herein lies the problem. Any deviation, such as mid-course corrections for gravitational perturbations from other celestial bodies, demands additional fuel. The Tsiolkovsky rocket equation, delta V equals VECE times the natural logarithm of m0 over mf, where delta V is the change in velocity, VE is exhaust velocity, and m0 over mf is the mass ratio, illustrates the exponential fuel requirements. For a round trip, the fuel mass would exceed the spacecraft's payload by orders of magnitude, rendering human missions impractical. Moreover, the temporal aspect exacerbates this. Astronauts would endure months in microgravity, leading to muscle atrophy, bone density loss, and cardiovascular deconditioning, effects documented in long-duration International Space Station (ISS) missions. Studies from the European Space Agency (ESA) show that after 6 months in space, astronauts lose up to 20% of their bone mass, equivalent to decades of aging on Earth. Recovery upon return is incomplete, and for a Mars mission without return options, this becomes a one-way ticket to frailty. But distance is not merely spatial, it is communicative. Radio signals travel at the speed of light, imposing a delay of 4 to 24 minutes one way, depending on planetary positions. In emergencies, real-time assistance from Earth is impossible. Imagine a solar flare disrupting systems. Decisions must be autonomous, yet human error rates in isolated environments, as per NASA's Human Factors research, skyrocket under stress. Even if we could bridge the distance, space itself is a radiation inferno. Beyond Earth's magnetosphere, cosmic rays, high-energy particles from supernovae and galactic sources, bombard everything. On Mars' surface, lacking a global magnetic field and possessing an atmosphere only 1% as dense as Earth's, radiation exposure is catastrophic. Data from NASA's Curiosity rover indicates that during the transit to Mars, astronauts would absorb approximately 300 millisieverts, MSV, of radiation, equivalent to 15 times the annual limit for nuclear workers. On the surface, annual doses could reach 200 to 300 millisieverts, far exceeding Earth's background of 2 to 3 millisieverts. The Health Physics Society reports that such exposure increases lifetime cancer risk by 5 to 10%, with acute effects including nausea, immune suppression, and cognitive impairment. Shielding solutions? Water or polyethylene barriers add mass, violating the rocket equation's constraints. Underground habitats on Mars might mitigate surface radiation, but excavation requires machinery that must first survive the journey. Galactic cosmic rays, GCRs, composed of heavy ions like iron-56, penetrate most materials, causing secondary radiation cascades. A 2019 study in Nature Astronomy modeled that even with advanced shielding, brain tissue damage from GCRs could lead to dementia-like symptoms after months of exposure. Furthermore, solar particle events, SPEs, eruptions from the sun, can deliver lethal doses in hours. Without predictive accuracy beyond a few days, as per NOAA's Space Weather Prediction Center, crews lack reliable warnings. Historical events, like the 1859 Carrington event, would fry electronics and expose humans to radiation levels exceeding 1,000 millisieverts in unprotected space. Biological countermeasures, such as radioprotective drugs, remain experimental. Amifostine, tested in animal models, shows promise but induces severe side effects. Gene editing via CRISPR to enhance radiation resistance? Ethical and technical hurdles abound, with off-target mutations risking unforeseen health issues. Propulsion technology stagnates as a barrier. Chemical rockets, with specific impulses around 450 seconds, are inefficient for interplanetary travel. Nuclear thermal propulsion, NTP, promising higher efficiencies, up to 900 seconds, faces regulatory bans due to proliferation risks and environmental concerns from radioactive exhaust. Ion thrusters, like those on NASA's Dawn mission, offer high efficiency but low thrust, extending travel times to years. Untenable for humans. VASIMR, Variable Specific Impulse Magnetoplasma Rocket, hyped by Ad Astra Rocket Company, requires gigawatts of power, far beyond current solar or nuclear sources in space. On Mars, In Situ Resource Utilization, ISRU, proposes extracting propellants from the atmosphere or regolith. Carbon dioxide could be converted to methane via the Sabatier reaction. CO2 plus 4H2 yields CH4 plus 2H2O. However, hydrogen sourcing demands water ice electrolysis, and Mars's polar ice is contaminated with perchlorates, toxic compounds that complicate extraction. A 2023 Journal of Geophysical Research paper estimates that scaling ISRU for a return mission would require infrastructure equivalent to a small refinery, vulnerable to dust storms and seismic activity, Marsquakes. Energy generation poses another impasse. Solar panels on Mars receive only 43% of Earth's insolation due to distance and atmospheric dust. Dust storms lasting months can reduce output by 99%, as experienced by the Opportunity rover in 2018. Nuclear reactors, like kilopower prototypes, provide steady power but risk contamination and require heavy shielding. Sustaining human life on Mars demands closed-loop systems recycling air, water, and food, technologies far from maturity. The ISS's Environmental Control and Life Support System, ECLSS, recycles 93% of water but relies on resupplies. On Mars, no resupplies mean 100% efficiency, an engineering fantasy. Atmospheric composition. Mars air is 95% C, O2, with trace nitrogen and argon, toxic without processing. MOXIE, NASA's oxygen extractor on Perseverance, produced 5 grams per hour, insufficient for a crew. Scaling to support 4 astronauts requires megawatts of power and years of operation. Water. Subsurface ice exists, but drilling in minus 60 degrees Celsius temperatures with low gravity, 38% of Earth's, is arduous. Perchlorates in the soil, at concentrations up to 1%, are neurotoxic and thyroid disrupting, necessitating complex purification. Food production. Hydroponics or aeroponics could work, but radiation and regolith toxicity hinder growth. A 2022 study in Frontiers in Plant Science found that Martian simulant soil yields 50% less biomass than Earth soil, even with amendments. Nutrient cycling fails without a balanced microbiome, leading to deficiencies. Waste management. Human waste must be recycled, but pathogens thrive in confined spaces. Psychological strain from odor and confinement amplifies issues, as seen in analog missions like HYCS. The human element cannot be ignored. Isolation, confinement, and delayed communication foster psychological disorders. NASA's behavioral health studies on ISS crews reveal increased rates of depression, anxiety, and interpersonal conflict after months in space. In a Mars habitat, crew dynamics could fracture under stress. Analog studies, such as Mars 500, simulated 520 days of isolation, resulting in sleep disturbances and reduced performance. Extrapolate to permanent settlement. Generational conflicts, resource scarcity, and the absence of Earth's biodiversity could lead to societal collapse. Ethical dilemmas arise. Who governs? International treaties like the Outer Space Treaty prohibit sovereignty claims, yet resource disputes are inevitable. Reproduction on Mars? Low gravity's effects on fetal development are unknown, with animal studies showing skeletal malformations. Finally, the fiscal abyss. NASA's Artemis program, a precursor to Mars, is budgeted at $93 billion through 2025, with delays rampant. A human Mars mission, per a 2020 National Academies report, could cost $200 to $500 billion, exceeding global space budgets. Private ventures like SpaceX's Starship promise cost reductions, but reusability in deep space remains unproven. Economic models from the Brookings Institution indicate that without immediate returns, for example, mining helium-3, speculative at best, investment wanes. Political will fluctuates, pandemics, wars, and climate crises divert funds. Climate change on Earth demands trillions in mitigation. Why allocate to Mars when our home planet teeters? A 2024 IPCC report underscores that resources for space colonization detract from terrestrial sustainability. As we conclude, the evidence is unequivocal. The confluence of physical, biological, technological, and socioeconomic barriers ensures that humanity will never set foot on Mars in a meaningful, sustainable way. This is not defeatism, but realism grounded in science. Instead, let us redirect our ingenuity toward preserving Earth, the only haven we truly have.